Okay, so here we are on question number 4. So first of all, some people were very confused by the whole string causing the ball to go. Okay, this was originally based on a question that asked about springs. We have not covered springs yet. That's going to come up real quick here. But I just use string here. Some people somehow try to make it a pendulum. That's fine as long as you got 40 degrees and 15 meters per second. Okay, those are the two key pieces we need to carry away in here. Because when that happens, what we expect is this ball to really go flying. Okay, this is a pretty quick speed here at a pretty good angle. Okay, and by the way, it left the string at 2 meters. Okay, so we're going to use all those facts, and our goal is to find dx. Okay, so let's take a look at that and see what is the average acceleration of the ball while getting hit by the strings. Okay, so notice this says average, which is different than our graph question in question number 1. Okay, so we can't like graph the impulse of the, we don't want to do any of that kind of stuff. That would be fairly tricky. What we can do is some pretty straight kinematics. Okay, so I'm going to try to find something. Notice I don't have time up here at all. So I'm going to try to avoid the whole time situation. Okay, so now I know it went from 0 to 15. Okay, and I'm trying to solve for acceleration, and it did all of this in 0.3 meters. Okay, so little algebra, make sure we're doing our squaring and square roots when appropriate. Okay, and we get a fairly big number. Okay, so right, not everything accelerates at 9.8. That is only when things are dropped. You get hit by a tennis racket, things are going to move a little bit differently. Okay, so this ball goes very fast, very quickly. So this is a fairly good serve for a hit here. It's also 2 meters high, which is kind of, for me, it's right at high level. Okay, so next up, how far away did the ball land? Well, there's a reason why I gave you a bit of real estate here to work on this. Okay, so notice we didn't have time, and that's just kind of a thing I like to know. Some people, by the way, solved for time and then found a different way to find acceleration. That's fine, because we need to know time either way. So just like I said before, if I'm going to do a diagram, especially if they say for a force diagram, then I don't want to double up here. Okay, so I'm going to do a diagram here just for this one, where I want to take my 15 and I want to split it up into okay, so this is going to be 9.64. That is my velocity in the y, and this was 11.5. That is my velocity in the x. Okay, so now I can do my x's and my y's. So the first thing remember I said I'm trying to solve for time here, and the reason why I need to know these is because of our age-old equation here. Okay, these all have to be in the same direction. So if I know my acceleration in the y, which of course is negative 9.8, okay, then I can use my velocity in the y and my distance in the y, and I can solve for all of those. Okay, so it's going to end up on the ground, but it started a little bit in the air, and it started going fairly fast. Okay, remember we only want to do our velocity in the y. Okay, super important you have your signs right on this one. This was started up, it was traveling upwards, but it was being pulled downwards. It was accelerating downwards. So we need up, up, down in our signs. Okay, so once we do that, you can put it into the quadratic formula and you should get a time fairly close to that. Okay, so we have about 2 seconds here, 2.15 seconds. Okay, now we could do the same thing here in the X. Okay, but we've done these equations a few times before, and notice we're starting at the origin and we have no acceleration in the X. So we can just rewrite this as velocity in the X times time. We know time is 2.15 seconds. We know velocity in the X was 11.5. Okay, and so that should give us 24.8 meters. Okay, I saw some people wanting to take this same triangle here. Where am I going to draw this? The 0.3 meters, and they tacked on that little extra 0.3 times the cosine of 40. I added that to this. Okay, that's the power of a diagram. If you call this your origin, okay, then I would accept that as your answer. But I would need to see that work laid out somewhere down here or in your diagram, okay, to answer that question. All right, okay. So I hope that helps everybody and that you come to class with some questions surrounding these.